Okay, so we're going to take a little break from related rates today. We'll come back to it on Monday. So the homework that was assigned at the end of Monday's class, the related rates homework, that's also the homework for next Monday's class. Okay, so that homework from the scanned pages in your packet is not due until Wednesday of next week. Just wanted to make that clear. All right, and then upcoming things, you have a take-home quiz. I'm going to give you a take-home quiz on Wednesday. Covers classes 26 through 30. And then on Friday, you have a related rates in-class quiz. You already all have the quiz. It's the first page of your packet. Yeah, so the in-class quiz is going to be a group quiz. You can work with your table mates and your classmates. It's one of the problems from the photocopied related rates problems. So you have the problem ahead of time. Feel free to look at it ahead of time before that class if you want to try to set it up ahead of time, get some ideas. It's just one problem, and you also have the answer to the problem at the bottom of the next page. Okay, so I'm not going to help you figure out how to do it. You need to figure it out on your own, but you'll know when you've gotten it. Okay. That's for the in-class quiz, in-class related rates quiz. That is Friday next week. Okay, so it's just the first page of your packet. Okay, so for today's class, we're going to look at two powerful approximation techniques that are used in applied mathematics when a function is just too complicated and messy to work with. Okay? So if you can imagine just the biggest, baddest, ugliest function you can think of, like just imagine like a giant fractions and fifth roots and craziness, right? Okay, so you do not want to deal with it. Like you look at it and you just go, ugh. So maybe you could just use a simpler function, but that has similar behavior to this awful function that you don't want to deal with. So that is actually very possible, at least on a small scale. Okay? You can replace a really complicated function with a really simple function that approximates it on a small scale. So what's the sort of simplest kind of function that we typically work with in this class? A linear function. A line. Okay, so here's a big, bad, ugly function, the square root of 1 plus x. I know that one's actually not that bad, but before calculators, it was a big pain. And we're kind of going to do a simple-ish one to show you the idea, and then you can apply it to more complicated ones. So let's build a linear function, L of x, that behaves similarly to my ugly function f of x, which is the square root of 1 plus x. We want it to behave similarly near x equals 0. That's sort of the region I'm interested in. It might not be a perfect approximation everywhere, but near 0, it will be good. Okay, so I have two requirements. Okay, first thing I need is that the function itself and the approximating function have to have the same value at 0. Okay, if I want them to be approximate around 0, right at 0, I'm going to make sure they are exactly the same. Okay, so what is f of 0? 1. So if you plug a 1 into that, we get 0. Now L of x is my linear function. So let's just call it ax plus b. So we've got two, is what not 0? Oh, f of 0, you're right. Sorry, it's 1. Yeah. F of 0 is 1. Thank you. Okay, so L of x, my linear function, is ax plus b. Got an unknown a and an unknown b. I just have to figure out what a and b are, and I'll have the linear function. Okay. So if f of 0 is 1, I want to make sure L of 0 is also 1. If I want it to be close near 0, I should make it exact right at 0. Okay, so L of 0 is going to be a times 0 plus b, which is Yeah, it's going to be 1. But if you plug 0 into this formula, what do you get? B, yeah, which has to be 1. Okay, good. So I now know B. That's handy. Okay. To figure out A, well, if I make the function itself match at 0, my function and my line have to be the same when x equals 0. I'm also going to make their derivatives match. Okay, so let's see, I'm going to write out f of x here. Square root of 1 plus x. What is f prime of x? Yep. Yep. You just do the power rule. The derivative of the inside is just 1 in this case, so the chain rule is not, I don't need to write down the chain rule. Okay, and then what do I get if I put a 0, because x equals 0 is the value I'm interested in here. What happens if I put a 0 in there? What do you get? One half. Yeah, you put in a 0 for x. 1 plus 0 is 1. Right? 1 to the anything is 1. So 1 to the negative 1/2 is 1. And then you multiply by 1/2 and you get 1/2. Okay. All right, so if f prime of 0 is 1/2, I'm trying to make a function that approximates f at 0. So I made the function itself and the line match at 0. Now I'm going to make their derivatives match at 0. So I'm going to come over here and I'm going to find out L prime of x. So if L of x is ax plus b, what's L prime of x? Just a, yeah. So L prime of 0, what do you get if you plug a 0 into that function? You get 1/2, yes, I have to force it to be 1/2, but just looking at the formula, L prime of x equals a. Don't think about the 1/2 for 1 second. What do you get if you put a 0 in there for x? Where are you getting 1?
Just plug a 0 in for x, you got b.
That's not the derivative. I'm plugging into the derivative. L prime of x equals a. You get a, yeah. Caitlin, can you explain how you get a? Right. L prime of x is a. There is no x to plug in a 0 for. It's a constant function, right? It looks like this at a height of a. No matter what x is, you get a. It's like saying L prime of x is 5, right? No matter what x I plug in for x, you get the constant. And then I know that I have to force it to be 1/2 because I want it to be the same as f prime of 0. Okay, so by making the function and the line have the same value at x equals 0 and the same derivative at x equals 0, I figured out values for a and b. Right? So my linear approximation, L of x, my a value is 1/2, 1/2 x plus b, which is 1. So to summarize, this is how we built the function. We started by making our big bad function, and our linear function had to have the same value at x equals a single value, x equals a. And then we had to make the derivative of our big bad function and the derivative of our line have the same value at that same single x value, x equals a. And that's it. We call this a linear approximation or a local linearization of the function at x equals a. So let's just take a look at a quick animation. So here, the blue curve is the square root of 1 plus x. That was what I was trying to approximate with a line at x equals 0. And this green line is 1/2 x plus 1. Right? See, it's got a y-intercept of 1. It's got a slope of 1/2. And then when I'm near 0, I'm going to slide this over here. When I'm near 0, see how the value of the y value on the line and the y value on the curve are almost identical. They're only off by a little bit. When I'm near 0, it's almost impossible to distinguish the green line from the blue curve. So that's the idea. I can use the line, which is much simpler than the square root function, as a substitute. As long as I'm near 0, the y values are really, really close, even as I get pretty far away, right? 1.59 and 1.47 are still pretty close together. Okay, so in this local region near 0, almost indistinguishable. From finding the derivative is just the slope of the tangent line. This, yeah, so this is finding, yeah, so what special line did we find? The tangent line, yeah, it's the tangent line at 0, yeah. So we often call the tangent line at a given point, which I know you all know how to find, right? The local linear approximation. Yeah. Yeah, if you go further away, right? If I put B like all the way out here at 8, right? Now this is a terrible approximation. Yeah, so I have to know I'm going to be near 0. Yeah. So I made the functions match at 0 and I made the derivatives match at 0. And I got a line that's pretty good approximation, right? What if you needed a better approximation? You could use a quadratic. Yeah, you could use a quadratic function to be your approximation. And then you'd make the function value match, the derivatives match, and what? The second derivatives match. Yeah. You're going to do that in your activities. All right, you can go ahead and get started.